This video is going to explore two different ways to solve stoichiometry problems using an approach called dimensional analysis and one called BCA tables. Obtaining quantitative information from a balanced equation, that's what stoichiometry is all about. This chapter began by looking at the information within a balanced chemical equation, went on to do conversions between mole, mass, and number of particles. When it moved on to empirical formula analysis, notice that didn't include a balanced chemical equation. You don't know the balanced chemical equation. You're doing conversions between mass and moles, but you don't have a reaction that you're working from. With stoichiometry, you're back to having a balanced chemical reaction. There's different kinds of questions that you can address involving stoichiometry. And when we look at the different questions and skills within this chapter, stoichiometry is really paramount. It's a huge idea within this particular course, and there's a lot of different ways questions can be posed. Dimensional analysis and use of BCA tables are two ways both will work to solve stoichiometry problems. The information within a balanced chemical equation, we have the balanced equation, the quantitative information. We can interpret the reaction in terms of the molecules that are present. 2 molecules of H2 react with 1 molecule of O2 to give you 2 molecules of H2O. Or you can scale it based on Avogadro's number and discuss that in terms of how many moles that you have. 2 molecules react with 1 molecule, or 2 moles of molecules react with 1 mole of molecule. The coefficients within the balanced chemical reaction are telling you how the moles combine with moles, or how the molecules combine with molecules. They're not telling you how grams combine with grams. We need to convert from grams to get into moles or number of molecules, because that's what our recipe is telling us. Within this description here of problem solving for stoichiometry problems, notice the first step would be to convert what you're looking at in terms of the reactants, let's say their gram amounts, to determine how many moles that you have. You'd be using the molar mass for that. Make use of the coefficients within the balanced equation. And then if you need to get back into grams, you'd use another molar mass. This description right here of going from grams to moles, using the balanced chemical equation, and then from moles to grams, that's true whether you're using dimensional analysis or a BCA table in your problem solving approach. Here's a typical stoichiometry problem. How many moles of H2 are required to completely react with 50.8 grams of N2? So we begin with a balanced chemical equation. This is a dimensional analysis approach. This would be the different stages that match up with this protocol here. Convert from grams to moles. This would be how many moles of N2 that we have. 1 mole is 28 grams, that's the molar mass. We use the information in the balanced equation. The coefficients. The coefficients are describing a ratio, a proportion of how much N2 you need for every H2, or how much H2 you need for every N2. So the coefficients are describing a ratio, a proportion, and that's used to get our answer. Here's another one that can be solved with dimensional analysis. How many grams of NH3 are produced when 28 moles of N2 react? See if you can set that up, use the previous example as a model, and see if you can go through the different steps within the protocol here as needed. This would be my setup. So we begin, it tells us the value already in moles. Let's use the information within the balanced equation and see the proportion. 2 moles of NH3 for every 1 mole of N2. Convert back from moles to grams. 952 grams of product would be the answer. How about this one? Hydrogen gas reacts with oxygen gas to produce water vapor. When 10 moles of H2 is added to 7 moles of O2 in a sealed container, all of the hydrogen gas is consumed. What remains in the container? Start with a balanced chemical equation. For this one, I'm going to explain how a BCA table will work. So we have a balanced chemical equation. BCA stands for before the reaction, what changes during the reaction, and what's after the reaction. Before, it gives us the information. We have 10 moles of H2, 7 moles of O2, and we don't have any H2O within the container. How do things change? Well, it says that all 10 moles of H2 are used up. All of the hydrogen gas is consumed, and we have none of it left over. How about the O2? How did that change? It began with 7. What happened to it during the reaction? Well, the coefficients are 2 to 1. 2 moles of hydrogen for every 1 mole of O2. That's what the coefficients are telling us. So if 2 goes with 1, 10 moles of H2 would be how many of O2? Simple proportion or simple ratio. You can cross multiply and divide, or you probably can do that one in your head and see that 5 moles of O2 were involved. Tell me about the H2O. Work out the change line for that. To solve it, you may have done this. 2 moles of H2, 2 moles of H2O. The coefficients are the same. 2 moles of H2 goes with 2 moles of H2O, so 10 would go with 10. How about this other proportion? Let's say you did the coefficient of 1 and 2. 1 mole of O2 produces 2 moles of H2O. So if you had 5 moles of O2, it would give you 10. Either way would work. In fact, all of the relationships have to work. Okay? All of the relationships within the change line, once you get one value, you can get all the other ones because the coefficients are your guide. For the ones that are reactants, I'm going to put negative signs to show those are getting used up. The product gets a positive sign, and then I'll just put those together and see that I started out with 7, I used up 5, I've got 2 moles left. I started out with 0, I added 10, I've got 10 moles produced. That's what remains in the container. Here's the description within the text for the different features within the table. The key thing that students ask about their struggle is the change line. The change line is a mole ratio that reflects the coefficients. The coefficients, after all, say 2 of these react with 1 of these to produce 2. 2 hydrogen gas plus 1 oxygen gas to give you 2 H2O gas. So the ratio of 2 to 1 to 2, we've just changed that and rescaled it. 10 to 5 to 10 is the same as 2 to 1 to 2. That's the information that the coefficients are telling us. I like this description I found on YouTube of a high school teacher that does a really good job, in my mind, talking through a BCA table. So let's see what we can learn from her.
In these stoichiometry problems, we're going to look at what you do when you're given a mass instead of moles to start out the problem, or a situation where you need to end in units of grams. Remember, for the BCA table, we have to compare units of moles because what we're ultimately trying to compare are number of particles. Those coefficients give us the ratio of particles needed to make our product. So in this problem, we are given 50.8 grams of nitrogen. And we need to the first step before we can use our BCA table is to figure out how many moles of nitrogen that is. So I'm going to set up a proportion off to the side here. Remember, we're going to use molar mass to convert from grams to moles. And for N2, the molar mass is 28 grams in every 1 mole. And we don't have 28 grams, we have 50.8 grams. And we want to know how many moles that is. So if I cross multiply 28x equals 50.8, and if I divide both sides by 28, x is equal to 1.8143 moles. And I'm going to keep a few extra decimal places until I get to the end of my problem. I won't round really well until the end. So it tells us that's moles of nitrogen. So before, our starting point is 1.8143 moles of nitrogen. And we're going to use all of that in the reaction because it says completely react. Next, I'm going to look at that mole ratio that comes from my balanced chemical equation. There's a 1 in front of the nitrogen and a 3 in front of the hydrogen. That's saying for every 1 mole of nitrogen that reacts, 3 moles of hydrogen have to react. So if, in my specific example, 1.8143 moles of nitrogen react, 3 times as many particles of hydrogen, 3 times as many hydrogen molecules have to react. So I'm going to take that 1.8143 and multiply it by 3. So I just figured out that I have to use up 5.4429 moles of hydrogen. So that means I have to have started with at least 5.4429 moles of hydrogen. I'm always going to start with 0 moles of product. And it says that I created, for every 1 mole of nitrogen, I created 2 moles of ammonia, NH3. So 2 times as much as the hydrogen. So I'm going to take that 1.8143 and multiply it by 2 to get 3.6286. I created, again, twice as many moles of NH3 as I used up moles of ammonia. So after my reaction is complete, I have completely used up the nitrogen, I've completely used up the hydrogen, and I have created 3.63 moles of NH3. So now it's time to identify what exactly the question was asking me. The problem says, how many moles of hydrogen? So moles of hydrogen, under my hydrogen here, would be this number. That's how many moles of hydrogen had to react. But I want to give my answer with three significant figures because my given had 3 significant figures. So my final answer is 5.44 moles of hydrogen reacted with 1.8143 moles of nitrogen. We're going to look at one more example. In this problem, we start with moles of nitrogen, and we want to know grams of ammonia. So since we start with moles, we don't need to do any conversions to get into moles. We can start by using our BCA table right away. So it says 28.0 moles of nitrogen react. The problem doesn't mention anything about hydrogen, so I'm just going to assume that we've got excess hydrogen, and usually we'll assume no product to begin with. So 28 moles of nitrogen react. All 28 of those moles of nitrogen are gone. Now time to use the coefficients. For every 1 mole of nitrogen, 3 moles of hydrogen are formed, 3 times as many. So I'm going to take 28 times 3, 84 moles of hydrogen are reacted. And for every 1 mole of nitrogen that reacts, 2 moles of ammonia are formed. So I lost 28 moles of nitrogen. I'm going to gain 2 times as many moles of ammonia. So 28 times 2, I've gained 56 moles of ammonia. So afterwards, there's no nitrogen. There's still excess hydrogen left over, and there are 56 moles of NH3 formed. Now the problem asks me for grams of NH3. So I'm going to have to do a little conversion to get these moles of NH3 into grams using the molar mass of NH3, which is 17. I'm going to set that up. There are 17 grams of NH3 in 1 mole. But I don't have 1 mole. I actually have 56 moles, 56 times as much. And I want to know how many grams that is. So it's going to be 56 times 17. So X, in this case, is equal to 952 grams of NH3. So these problems are really just a combination of our BCA tables and converting back and forth between grams and moles.
So the examples that the teacher shown within the video were the same ones that I had to begin this video with dimensional analysis. So we had 2 different equivalent procedures shown. Here's one that matches up the BCA example that I worked through, where these were in mole amounts. This would also be applicable if instead of looking at mole amounts, we talked about the number of molecules that were present. Our coefficients can be in terms of moles, or they can be number of molecules that are present. So this is also consistent with the BCA table. Question for you: what would be the contents of the container after the first 4 molecules of H2 reacted? So instead of going before all the way after, what's in the container after the first 4 molecules of H2 reacted? This kind of question illustrates what I think the value is for a BCA table. If they're both equivalent, which one do we choose? They both work, but if the question is asking for more than one value, this is asking for the amounts that you would have potentially for both of the reactants and the product. If you need to figure out more than one thing, I like a BCA table because all the answers are going to be within the table. So what I'd like you to do is see if you can answer that. I would be setting up a BCA table. That might be the way that I'd recommend it for you as well. What would be in the container after the first 4 molecules of H2 reacted?